everyone. As Dave said, my name's Tom Shea. I'm a senior data scientist at Gousto. I'd like to introduce our four-part talk today called The Data-Driven Supply Chain, where three other speakers and I will discuss the various ways in which we use data science to grow and optimize our supply network. And when I talk about supply here, I mean all of the components relating to the physical production of our goods and services. So forecasting, planning, operations, logistics, shipping, physical factory configuration, mechanical automation, and the optimization of our collection of factories as one unified system. I really like working in physical product because it makes all the problems a little bit harder, but they feel more tangible when we solve them. So, just like to quickly chat a bit about the company, what our company is and what we do. So Gousto is a meal kit company delivering boxes of fresh produce and ingredients right to your doorstep. And we've been operating for nearly 8 years. Our founder did appear on Dragon's Den in 2013, so you may have seen him there. And Gousto's ambition is to become Britain's most loved way to eat dinner. And we really strive for three main things in our product, which we hope differentiates us from some of our competitors and other ways of eating dinner as well. So first of all, variety. We have a big team of professional chefs and food innovators who are working continuously to invent a whole new menu of recipes to order from every week. This means you'll always be able to find something new to try and explore every week while still being able to rely on your absolute favorite flavors being available. And we've got cuisines from so many different nationalities represented on our menus. We also have an excellent team of data scientists supporting this menu curation algorithmically, and they optimize for things like personalization, preference, and diversity in the menu. Next, it's quality. So we strive to curate our supplier relationships to ensure our ingredients are as fresh as possible and of the highest quality possible. We're also working continuously to minimize the non-recyclable packaging in our boxes. And in fact, we recently attained B Corp status as a corporation, which validates some of these environmental efforts. And finally, it's simplicity. So we aim to make the unboxing experience and the cooking experience delightful and convenient by including very achievable instructions in the box and in the app. So I've been cooking some pretty complex stuff since starting at Gousto, and I'm pretty impressed with how easy it feels. So we have a phrase at Gousto that we're a data company that loves food. And this is meant to convey that data is really at the core of everything we do in every domain of the company. This means that there's extreme buy-in and investment from all sorts of stakeholders, all the way up to the leadership team for what we do as data professionals. It also means there's a lot of work to do. So from building performant terascale ETL pipelines and real-time feature stores to prototyping proofs of concept of new and disruptive ML models, to standing up new data-driven cloud applications at light speed and maintaining and monitoring them as easily as possible. To running rigorous A/B testing and experimentation protocols to validate and prove our impact, and also to building self-serve analytical tools to support anyone in the business to be more data-driven themselves. So for these reasons, I think Gousto is a fantastic place to work as a data professional who wants to grow their career. And luckily for you, we're hiring big time, so please get in touch. A quick word on how we structure our organization in order to support our data professionals to succeed. So we operate a tribe model where a tribe is a collection of multidisciplinary teams all unified towards a common goal. We really believe in ownership at Gousto, which means being empowered to design, ideate, influence, change, build, iterate, and make critical decisions about your squad's products. Each of these, the teams in the tribe are called squads, and they own specific products or services. We have embedded data engineers and analysts and scientists in each squad, which allows individuals to specialize, but also have the flexible option to transition to a new problem domain if desired. And we really like to sort of, as a culture, try to preserve some of the startup mentality of moving fast and trying things and taking a scrappy approach to driving impact. This means we have a strong bias for simplicity where we can, which I'll give an example of in my talk. So let's move on to some data science. In supply, we're constantly making product decisions. And each of these decisions is characterized by risk and reward. This ranges from each minuscule feature change we might ship all the way to planning entire roadmaps for quarters and entire years. So my thesis is that we really want to add evidence to all of those decisions. My opinion is that more information will always improve outcomes. So I'll be talking about a new system that we built recently and how we used offline back testing to prove its efficacy before going live and de-risk the critical path to getting there. Cool, so just a quick introduction to myself. I'm a generalist with a pretty diverse background. I did just one degree in biochemistry and physics in the States. Then I became an immunologist in an academic setting. At some point, it dawned on me that I really didn't like that. So I made the switch to tech and started out as an analyst by convincing some tech people at a job fair that I could write SQL, which worked out well. Then I did quite a hard pivot and started my own hardware company and learned a lot about why my ideas maybe weren't so great and how to fail quickly. And then finally, I became a data scientist. I've had a few roles as a data scientist and now I've been at Gousto as a senior data scientist for 1.5 years. My personal motto is move fast and test things, which basically means keep experimenting, keep gathering data, keep trying to add evidence, and always revise your understanding of the world based on that evidence. Don't be afraid to break stuff. Okay, so finally, some data science. We do quite a bit more what I would consider operations research than conventional machine learning in supply at Gousto. I'd like to just introduce a concept here and describe it, and it'd be great if you could keep this in your minds and think about how it applies to the rest of the talk. So the concept is Pareto efficiency, also known as Pareto optimality. This concept arises frequently when you've got a multi-objective optimization system, especially when there are trade-offs or interactions between your objectives, which is a very realistic situation to be in. On this plot, you've got two axes, which represent some arbitrary cost functions that we're seeking to optimize, so function 1 and function 2. The position of each point on the plot describes how well it scores in terms of these objectives. So lower is better, closer to the origin is better. So this plot describes our objective space. And if you were to exhaustively search objective space for solutions, you would find some suboptimal solutions indicated by these points up here, so further away from the origin. You would also find what's called a Pareto Front, which is this line here. Which indicates a global optimum surface over your multiple objectives. This means you can say that at this front, you can't improve on one metric without sacrificing another. Of course, this plot is in 2 dimensions, but the concept extends to any number of objectives. So if we can find the Pareto front in our objective space, we can be quite certain that we found optimal solutions, and then we can have informed discussions about the trade-offs between objectives in an applied fashion. And if we indeed find solutions that are superior to our previous understanding of the Pareto front, we can quantitatively ascertain that they're superior, and this makes any decisions we drive from this unambiguous. In terms of finding the Pareto front, you can brute force search the objective space if you've got enough compute, or if you can design your algorithms well enough. You could sample from it, or you could use a more informed search algorithm to detect it. But okay, cool. So keep that concept in mind, please. Now, I've spent the past year thinking about what might seem like quite a simple question, but there are some not so simple considerations that go into it. So the question is, what is the best factory to fulfill this customer's order? This is a multi-objective optimization problem, and it's become much more salient over the past year as Gousto has scaled enormously. So 1 year ago, we had 1 factory, and by the end of 22, we'll have 5. So this is a huge step change in complexity, and it means that this question in this area has become more of an opportunity for optimization. So on the left, you can see a map of the UK where we operate with a representative illustration of where our factories are in red, and our customer population, which is naturally proportional to the UK population density. So this sort of represents one of our first objectives in this question. We want to fulfill each customer's order from the factory closest to the customer. This is pretty intuitive. This cuts down on mileage and emissions and allows customers to get their orders as quickly as possible. But it's not our only objective. Not all of our factories are created equal. So first of all, different factories have different capacities because they're different sizes. So we need to take this into account as an objective, that there may be surplus capacity at certain sites that we want to use up. And this also plays into like cost and emissions considerations. And it gets even more complex than that. So if you consider each of the colored dots under the factories in this diagram to be representative of the list of ingredients that each factory hosts each week, not every customer order can be fulfilled at every location. So we need to take this into account as a constraint in our algorithm. Incidentally, we have another algorithm which ultimately decides which ingredients to host at which site. So yeah, we're working on a lot of things simultaneously. So we really wanted a simple, interpretable, modular, and easy to maintain system to optimize across this multi-objective space. So we elected to go with basically the simplest design we could think up here. And this is kind of like one of the points I really want to get across is that simplicity can be very good in data science if it drives measurable impact. So this system operates on the basis of a single order. At any time, we can just invoke this function and return what we believe to be the optimal factory decision for that order based on the most recent information available from our operation. So all of our operational systems are spewing out data and we're ingesting it, and that represents the state of our operation, and we're making a locally optimal decision based on that. So the system consists of multiple objective modules, each of which is a formalization, basically putting into code the objectives I just described and more. And each of these modules has a weight, which essentially multiplies the effect of that module. So these are, I like to think of these as the dials, which allow our stakeholders to control the system and try to amplify the business outcomes that they care about. After that, the different modules simply vote on a decision, and we take that as the optimal decision. So this is a very modular and easy to interpret design, which allows us to introspect the effect of any particular module or weight on the outcome and revise our decisions. So another key feature of this system that is a key principle in our design is that it's stream-based. So in an ideal world, you can batch process an operational decision like this. If you have all of the information that you need, your information complete, and that information state won't change, then you can simply process that entire batch and you can probably get a more optimal outcome. However, our customer orders arrive stochastically over a long lead time. So the new menu becomes available at some point, but customers aren't ordering until up to 10 days later. Their orders won't arrive until up to 10 days later. So their decisions, which we need to actually act upon, they arrive much earlier than that. And so, and in addition, like over that time window, the state of our operation can change. So the underlying data can change. So the idea here is that we want to be able to make a routing decision immediately when the customer chooses their order, and then revise it, have the flexibility to revise it intelligently as more information becomes available. So like moving from left to right, we've got an order creation event, and we're making a decision about, this is a routing decision to factory A. And then the model may revise its decision at a later time point when we invoke the function again, and it routes to site B. And ultimately, it progresses and flexes until we finally lock in that decision at the time point at which we go on to fulfill that customer's order. And this allows us to sort of drive our long lead time decisions out of these routing decisions, but also have the flexibility to respond to changing situations on the ground. So into some results. This is an example of a backtest that we did to demonstrate the efficacy of the algorithm before going live with it. And this is all based on real data. So we basically ingested a bunch of data from our operational systems and then used that and piped it through our algorithm offline outside of our production environment in order to assess how it would have behaved and performed. So what you can see here is kind of an animation of how this stream processing algorithm works. So let me just explain these plots. You've got 3 plots. Each one represents a different factory in our network. And the x-axis is essentially, I'm calling it skew initial abundance rank, but it's basically a representation of the inventory at each of those factories. Okay, as orders stream in and a quasi-optimal decision gets made, it decrements down the inventory position. So our goal here is to end up with 0 inventory because this means less waste, which is better for cost and environment. And it's quite hard to guarantee this when we don't have the full batch of information. We are not information complete at the beginning of this algorithm. However, as you can see, despite not having full batch info, this algorithm can continuously stream allocate orders to each factory, complying with our multiple objectives and constraints, and still successfully iterate towards inventory 0, which is a huge positive outcome for this algorithm. And finally, this was one of our more impactful results, which hopefully demonstrates that we did indeed break through the Pareto Front. Again, this was the same backtest on real customer data. And we're trying to show an improvement against our legacy system. So what we've done is we've run our legacy system, we've quantified all of our multiple objectives. So we have essentially a score for each of those objectives for our legacy system. This is over a backtest window, which is a number of months. And what you're seeing here is a metric which essentially describes the rate at which we're able to use our preferred courier. So just like our factories, not all of our shipping providers are created equal, and we would always prefer to use the courier which is quickest and has the lowest emissions and improves the customer experience the most. So this metric on the y-axis basically represents the rate at which we successfully use our preferred courier. Now, in this backtest, every other metric achieved perfect parity in terms of performance with our legacy system. And what you can see on this plot is that the variant system in red is strictly better than the legacy system on every single day in the backtest. Okay, so if you have a solution which is equivalent across every other objective in objective space and superior, strictly superior in one other objective in objective space, you have successfully broken the Pareto Front and you have come up with a superior solution in terms of your multi-objective optimization system. So that concludes my section of this. I'm now going to hand over to Dom, who is another one of our very experienced data scientists who has been at Gousto even longer than me.
Hi guys, let me just share my screen.
Looks good.
Cool, can everyone see that? Great. Hi everyone, so as Tom mentioned, I'm Dom. I've been at Gousto for about 1.5 years now. Actually, I started way back on the first day of lockdown 1, which was quite a weird experience. In my time here, I've worked on loads of stuff across the supply chain side of the business, including on one of the algorithms that I'm describing in detail shortly. And previous to this, I'd been doing similarly data sciencey things for British Airways and then McLaren Applied Technologies. So Gousto has roughly been doubling in size basically every year since before I joined, and the ongoing pandemic has ensured this trend isn't slowing down. Order numbers have continued to climb, and to meet this increase in volumes, we've had a really quite relentless focus on capacity. Of course, the most obvious method to expand our capacity is to open more factories, and indeed, as Tom mentioned earlier, we're kind of on the brink of opening a third Gousto factory alongside our third-party fulfillment center, with more to come in the future. However, this isn't the only way to increase capacity, and as data scientists, it's been our responsibility to create data products that help us get the best out of our factories that we already have. And in practice, this has meant that we're almost always optimizing for one thing: line throughput. the more boxes we can get down a production line at any given hour, the higher that line's weekly capacity is, and the more customer orders we can take on. And while this focus has served us really well for the past 18 months or so, our team has expanded in this time, allowing us more time to dedicate to each specific problem that we solve. And it's given us a great opportunity to expand the scope of our data products to optimize for multiple different and sometimes competing objectives. And while some data products, such as the order allocation algorithm that Tom has just discussed, have this kind of built in from the beginning, a lot of our data products that already existed had to be retrofit to achieve this. So what I want to talk to you over the next kind of 10, 15 minutes about is this journey, which we're really only now starting to get in earnest. So what else might we want to optimize for? So there are many things I can talk about, but there are two specifically that I want to go through today. So a big one is OTIF. So this stands for on time in full. And this is basically, did a customer's box arrive at the time specified with all the ingredients present and of good quality? You can probably imagine that this has a large impact on the customer experience and hence how well we retain customers. So it's a very important metric for us. Another important one is labor cost. Suboptimal warehouse processes can lead to redundant work being done, which in turn increases our labor costs and impacts our bottom line. And while throughput is, of course, one of the large things that can impact our labor costs, there are many other ways we can move the needle here. So before we go discuss about how we optimize for objectives, it's worth explaining one of our key operational algorithms, which I use to illustrate them. So Pickface optimization, or PFO as we abbreviate it, is concerned with how we set up our picking lines. And as you can see from my lovely mirror diagram on the bottom of the slide, customer boxes move down the line's central conveyor and come off at certain picking stations, where an operator will put in ingredients in a box using a pick by light system. And so what PFO does is it maps the ingredients to these stations, which is a process that we run once a week ahead of our new weekly menu. How we decide where we want to put the ingredients is informed by two intuitions and one objective. So our first intuition is that if we place ingredients on the line grouped by which recipes they are in, then we only have to go to at most one station to get that recipe's ingredients. And the second intuition is that we want the more popular recipes we place on the line more times, as it allows our routing algorithm more options to go to for a box which has that recipe. And as you'll probably guess, the main objective here is throughput. And in fact, our evaluation process for PFO solutions involves using our order routing algorithm, ORA, to simulate the routing of orders down the production line that is represented by a particular solution. And then we use some throughput-related summary statistics from this simulated routing to gauge the quality of the solution. And because PFO's base algorithm has the element of randomness, it means we can generate many different solutions and evaluate each of them this way to decide which is the best one. So how can we expand the remit of PFO to optimize for other objectives? So one thing we've already started to do in a limited fashion, and we're planning to expand on, is to choose how far along the line we're placing ingredients, depending on how much they weigh and how delicate they are. So for example, we sell bottles of wine as an additional marketplace item that you can get with your box. You can imagine that we want to avoid putting the wine in a box at the end of the line because it's liable to crush more fragile ingredients. And similarly, with more crushable ingredients, such as peppers, for example, we'd want to put them in right at the end to decrease the likelihood of them being crushed by heavier items. Indeed, way back when Gousto was actually first built and had its first production line, there are ingredients that were distributed down the line using this logic, and we only changed this when we decided we wanted to optimize for throughput instead. And so we can implement this logic by choosing which station to put a recipe on according to a distribution that we can choose dependent on the characteristics of the ingredients in the recipe. So the recipe includes, for example, a few cans and no easily crushable ingredients. They would get placed on stations according to the distribution on the left of the graph, putting it on early the line so it doesn't crush anything. Whereas recipes full of crushable vegetables might follow the distribution on the right and hence be more likely to go in towards the end of the packing process. And doing this for a lot of different recipes allows us to minimize OTIF. So another new feature of PFO that we've done quite recently is the functionality not to only map ingredients onto stations, but also decide where on those stations the ingredients go. So you can imagine a picker standing there and there's different locations where the stuff is and they can pick it up from different places. And this has historically been a lengthy manual process, which had scaled in time as Gousto had. So simply automating it has been quite a big win. However, never want to rest on our laurels. We've been thinking about how we can use this new capability to reduce our labor costs. So to understand how we might do this, consider the overlap between our menus week on week. While we might have a mostly fresh set of recipes every week, some ingredients will inevitably be on both the preceding and the current menus. So I have to admit, I haven't actually looked at the data for this, but I'd wager that every Gousto menu since day one has included garlic, for example. And because we have a new line set at the beginning of each week, there's a not insignificant amount of manual work to tear down the old line and set up the new one. But what if we could leave some ingredients in place week on week? After all, that we know that we're likely to have garlic, for example, on the menu every week, and that it's a popular enough ingredient that it may well end up on a lot of the stations. So by leaving it in place, we need to do less work to change over the line between the menus. And if we do this for lots and lots of popular ingredients, we can significantly reduce the manual work needed for this key operational process, allowing us to bring down labor costs over time. So how do we actually optimize for these things then? So there are two main ways we can do this. So the first way involves modifying the base PFR algorithm that generates the solutions. Changing the recipe placement distribution as described a few slides back is an example of this. We could also, for example, change like weight where we put recipes dependent on the number of SKUs that's overlapped with the same station on the last week's menu. And this could help with the line consistency that we just mentioned as well. So this is kind of our first way. And our second way leverages randomness and computing power to give us a large pool of solutions that we can evaluate in arbitrarily complex ways. So I mentioned how we use our order routing algorithm to evaluate PFA solutions using proxy throughput metrics. But we can extend this idea to evaluate against many different objectives. All we need is some method of getting from potential solution to an estimate of a desired metric of interest. So for instance, we could dive into our specific kind of like routing that we get and check how likely it is that we're actually going to be picking those heavy cans before the crushable peppers and derive an OSI score from this. And likewise, a simple comparison to the last week's line setup allows us to check the current solution for a line consistency score. And finally, we can put this together, weighting the metrics as we desire to choose an overall objective or an overall solution that we want to use. So another benefit of this approach is that it makes it easy to surface solutions that bias towards one objective or the other, perhaps even showing the whole set of Pareto solutions, as Tom mentioned earlier. Depending on how the following week looks, we might decide we want to, for example, focus on OTIF because we have lower order numbers and hence less need for high throughput. Or perhaps as an ongoing global pandemic, for example, and we're struggling to get the work numbers we need for our menu changeover process, in which case we might decide to pick a solution that prioritizes line consistency. But the ultimate aim really is that when I say we, I'm not actually referring to us as data science anymore, being asked last minute to bias our solution towards certain objectives, but instead the power is given directly to our operational stakeholders. And ultimately, they're always going to be better placed than we are to understand the needs on the ground, and if we can empower them to make the decision that's better than at the time, then I think we've really succeeded in our job as data scientists. So as I mentioned, this is really just the beginning of the journey. There are plenty of other objectives that I didn't mention that we want to optimize for, from increasing customer choice to further reducing food waste, not just within PFO, but within all of our data products. And of course, all these objectives have trade-offs with one another. Understanding these is key to having the confidence to choose between one solution or another. And this consideration actually brings me quite nicely to the next section of the talk. So my colleague Joe has been with Gousto for about a year, working with a variety of things to do with network optimization, and in particular our network simulation data product, which he's going to discuss today. So I hope you enjoyed my section of talk, and over to you, Joe.
Hello, so let me just quickly share my screen. Cool, so yeah, as Don mentioned, my name is Joe. After finishing a degree in engineering, I quite quickly realized it wasn't to me, and I made the switch to data science, where I completed my master's in data science and since then have not looked back. And yeah, so after that, I joined Gousto, where I've been for about a year. And I've been working on a number of problems, all of which pertaining to how we can get our network of factories working well together. So what I'm talking about today, I'm going to be talking about network simulation. Well, in a summarizing, the network simulates the data-driven decisions of our supply chain in order to investigate the effects of future business propositions. So what does that mean? Well, firstly, we have this these two words, so network and simulator. What do they mean? Well, firstly, network. So a network is a collection of factories as opposed to a single site operation. So obviously Gousto, as a large fulfillment company, we started off as a single site operation. However, we are moving away from that. We're getting more factories, and this is only something which is going to increase. And obviously with having a greater network, it obviously becomes a more complicated operation. However, it also leaves room for more optimization. And yeah, so secondly, simulator or simulations. What is this? Well, a simulation is essentially something which replicates a real world process and in a digital fashion. And what is a good thing about simulation is it allows you to test scenarios without having to implement them in real life, allowing for cheap experimentation. Cool, so that's what network simulator means. So data-driven decisions. Within Gousto, as Tom and Dom have mentioned, we have a number of different data products. A number of these data products make automated decisions on a weekly cadence, and really they can range from anything to, from creating a menu to deciding what are the optimal recipes to host at each site. And then final point to quick future business propositions. So there are two core future business propositions which were a big driver for the network simulator. So firstly is we want to have more recipes. As a business with Gousto, we want to be able to offer our customers anything they want, and to get there we have to obviously maximize the number of recipes we can offer. Until recently we had I believe a minimum of 50 a week, and now we offer at least 60 a week, but we are hoping to grow that in the coming years. Now obviously, as you would imagine, offering more recipes, it makes you need to host more ingredients across your supply chain, and obviously that on its own is quite a difficult problem, but it also introduces a lot of less trivial and less obvious problems. So for example, if we have 60 recipes now and we expand it on site which can only host 30 recipes, then that particular site can fulfill a far smaller proportion of the total recipes. And this in itself creates a lot of complications, and also downstream from there creates further complications. So yeah, just to highlight, there's a lot of kind of non-obvious problems to solve within our supply chain, which are easily examined using simulation. And the second of our future business propositions is more factories. So naturally, we're a fast-growing company, and naturally to do that, we have to open more fulfillment sites. Kind of what's going to happen if we have several more factories, but using simulation, we're able to do this. So to kind of tie back to the original definition and just to give a quick summary, essentially the network simulator is something which aims to simulate our weekly operation of our supply chain for sort of arbitrary points in the future which we can create. And this allows us to sort of answer critical questions and be able to plan accordingly. And cool, yeah, so that's what it is. Now, how does it work? So the network simulator is essentially an ensemble of existing data products within Gousto, and they are sort of integrated together. And each of these data products kind of has an output which will then influence the next data product in the chain. So it's very much one thing happens, it passes information to another product, that sort of gets processed, makes some decisions, and then it carries on going in a chain. Sorry. And also, I should note that each of these data products, which are integrated together in this sort of simulated chain, each of them are very valuable in the sense that they all exhaust quite a huge amount of information which allows us to kind of derive very valuable insights at different stages within our supply chain, and allows us to examine the stresses of what will happen if you know, we have 100 recipes and 10 factories. Yeah, kind of how that will affect things. So the first algorithm in the chain is something we use to create a menu. And within the scope of this simulation project, we typically use this to generate a menu of, I don't know, say 100 recipes, and then we'll be able to see how that impacts our supply chain. And so how this algorithm works is essentially it has a number of target variables, and it will aim to create a menu which sort of meets all of these targets. And these can range from things such as the average cost per meal or the proportion of vegetarian ingredients we want on a menu on a given week. Cool, so once we have a menu, we're then able to create a forecast. And the objective of this is to essentially create a forecast of what we believe a realistic week in the future, yeah, kind of what the orders will look like in that week, where the orders are composed of a selection of recipes and also add-ons if the user so chooses. Cool, and then so once we have this forecast, we know, or we have a good estimate of what the orders will look like in their contents. We can then figure out what are the optimal recipes to host at each site. As we've mentioned earlier, there is a bit of asymmetry in our factories. So some factories might be able to host all of our recipes. However, some factories might be able to host a far fewer amount. So as you can imagine, there's quite a lot of room to play with in terms of when and play factories in a way which fulfills our customers' orders as efficiently as possible. Cool. So once we know what recipes are going to be hosted at each site, we're then able to run the Pickface optimization algorithm, which Dom discussed earlier. And just to recap on this briefly, it essentially chooses where on the picking lines, where to put each ingredient. And it does so in a way which allows boxes to move down the line as efficiently as possible, to have as high a throughput as possible, which is the number of boxes we can fulfill in an hour. And once we know what our pick faces look like, we're then able to run our order routing algorithm. And what this does is it essentially takes a box and its contents and it decides what stations it should visit. And it will do so again in a way to maximize throughput and be able to get as much boxes down the line as quickly as possible. And finally, in this chain of data products, we then, we then have throughput predictions. So based on a number of operational inputs and the routing decisions of boxes, we are able to predict the hourly throughput of each of our production lines. Cool, so what does it tell us? Well, it tells us a number of things. However, I'm just going to touch on a few to sort of give a broad idea of what these things look like. So as I mentioned, we want to expand our recipes, and we also have a number of sites which can host different amounts of recipes. So obviously it's very important for us to be able to have a rough idea of how many recipes we can host at each site. And that is something that we can plan with the network simulator. As well as that, as I mentioned, we can predict the throughput. We can, predict this with a rough range of what our throughput might look like. And what is so crucial about this is if we have an hourly throughput, that feeds directly into our capacity at each site. So obviously that's a big thing. We want to know in a year's time, are we going to be able to hit this demand? Our hourly throughput is something which will feed very much into that and help us answer these questions. another big question we often get from stakeholders is how many orders would be routed to each site given a larger menu and a larger number of factories? Well, this plot here essentially shows sort of site by site what our target volume is for each site, what the number of orders routed to each site is, and also the eligible volume for each site. And so, for example, this plot here, we can see that, for this given configuration we ran, that we weren't able to route so many orders to site C, and these were going to be picked up by site D. And knowing this ahead of time, to plan our operation, able to have stresses which I apologize for the very corny image, as this is meant to represent data. But a big thing we got out of the network simulator is we're able to generate representative future data of what our operations will look like in a year's time. So, for example, we might want to know what will a site-specific forecast look like if we have more sites than we do now. Or we might also want to know what will the routing decisions of boxes look like if we have 150 recipes on our menu. We might want to see how many stations a box will visit and how will that impact throughput. And yeah, so to summarize, there's a huge amount we can deduce from the network simulator, and it's really sort of endless in terms of the things we're able to examine and the insights we are able to get. And yeah, so that wraps it up for network simulation. And given that's what I've been talking about for the last 10 minutes, I think it's only suitable that I hand over to Daniel so that he can discuss how we simulate the inner workings of our factories.
Cool, thanks, Jay. Let me just share my slides. Cool. Yeah, as Joe said, I'm Dan, and I'm going to be talking about simulating the inner workings of our factories. So by way of introduction, my name is Daniel Paddon. I'm a data scientist here in the Unbox tribe, formerly known as Supply, whereas, as the guys previously said, we sort of help our factories work as well as possible. Previously, I've worked as a data scientist in a couple of other places in retail analytics and financial services. So, talking about simulating the inner workings of our factories, well, why do we need to do that? So I guess, probably Gousto's strategy for the last, few years could be summed up by this image. As you've heard, we scaled from 1 to 3 sites last year, and that doesn't look, doesn't show any signs of slowing down. And you've heard that, the transition from 1 to N factories is a step change in the complexity of our operation. We now have to consider where each order is going to go, whereas previously that was just one factory. But within that, each factory offers a step change in the way that it works. So we now have to consider sites, which are vastly different in terms of size and scale, and which have varying levels of automation and different internal processes. And so that means that some of our old assumptions, probably won't hold for the new factories. And we as data scientists, we have to design systems which play well in all the different scenarios, both current and future. And we also have to support the business in operational planning. So as Joe described, we might need to know expected throughputs of the sites. We might need to know expected staffing requirements and things like this. So with that in mind, let me sort of talk you through a sort of typical data science workflow. And I can already hear people saying that, this is a little bit idealized and that nothing is as simple, but just bear with me. So imagine that, we're one of our data scientists at Gousto who's working on our recommender system. And we have a hypothesis that maybe we could improve our recommendations and better understand our customers' tastes if we, for example, add a new feature to our model. So maybe we collect some data, some attributes about our customer and the product. Maybe we collect, what we're ultimately trying to predict, those transactions, the customer behaviors. And then maybe we create a model, or more realistically, we import XGBoost And we train a model on that data, and tune the parameters until we think we have a model that fits our needs. And then we want to do an experiment, right? We want to validate that what we think works actually works. So we can select a representative subset of customers, and we can maybe route those customers to our version 2 of our recommender API for a few weeks, collect some data, and then analyze it. And hopefully we can establish stat sig, and say that our hypothesis works. And then maybe we roll it out. We roll that API out on SageMaker, for example, and we improve our recommendations for all our customers. Now, this is great, and it gives us data to validate that our approach works, or even that it doesn't work. And we can do things like quantifying the impact through the uplift that we might gain. But the problem is, as Tom said earlier, we deal with the physical world, and while that is very rewarding, it also comes with some challenges. So, for example, we can't A/B test on 10% of the factory. It's really hard to carve out a part of the process, such as the movement of stock around the warehouse, or the production line where our boxes get picked. Partly because, as it says here, real world processes aren't independent. If we're doing a recommender system, then it's probably a reasonable assumption that our customer browsing sessions are independent. But if we're doing stuff in the factory, then changing one part, for example, of the Pickface, with the algorithm that Dom spoke about, that will impact the rest of the production line. It will impact where orders can be picked. And even if we could split off part of the warehouse, maybe it has a feedback loop to some other part of the process. And then I guess another related problem, the final problem, is that unsuccessful experiments can be very expensive in the physical world. So if we mess up and we miss the outload times with our courier partners, then that costs us. It means our customers' boxes get delayed. That costs us in terms of reputation, and also in terms of refunds, and also it costs us wasted food. Maybe the food expires, or we have to waste something. And as a B Corp, that's something that we really don't want to be doing. So as a result, as data scientists, we have to be quite creative when we're designing our new solutions, and we have to maximize our confidence that what we're working on is going to work before we run a trial in the physical world. And so this is where we lean on simulation quite heavily. So what do I mean by simulation here? Or I guess there are a few different ways that you can approach simulating your problem, and I'll talk about a couple here in differing levels of detail. And I guess simulation doesn't have to be complicated. As Tom said, there's real value often in taking a simple approach, when it's appropriate. So, for example, in the top left here, here's a sort of low detail approach. So maybe we have like a reasonably standalone process. Maybe we're routing orders down the line, or maybe we're only interested in the directionality of the results. Does this metric go up or down based on a change? And then our simulation could be as simple as a for loop. Here we can loop through a list of customer orders, and play out the process and monitor some results. And we can get serious value out of that. But maybe we need a bit more detail. And so we use quite a lot a package called SymPy here at Gousto, which is a discrete event simulation Python library. And so in discrete event simulation, basically, you're simulating a process where you have you have a system, and events happen within that system, and they take a specific amount of time, and they occur at specific points in time. And each event that takes place, represents a change to the state of that system. And this is really useful because it fits nicely with a lot of the problems that we deal with at Gousto. So, for example, moving a pallet of stock around the warehouse is a discrete event. Your carrots went from point A to point B, and it also allows us to model interacting processes. So in this example in the middle, this is just some code from the SymPy documentation, and you can see we've got two clock processes, a fast one and a slow one, that interleave. And again, you can imagine that we might have fast and slow processes in Gousto that we want to model the interaction of. And then finally, there's the kind of really high detail but also high investment option, which is to use commercial software. So for example, AnyLogic, this is just a screenshot of an example AnyLogic simulation from the marketing material. But that that has a real sort of power to it and is really flexible. But sometimes that's overkill for your problem, and it's also definitely the most expensive of these options. So talking about simple simulation, let's look at an actual example from Gousto, albeit with simulated numbers. So here we're modeling this order routing algorithm that we have that sends different customers boxes to different stations. And if we look on the left, we've got a very simple setup where we initialize our list of stations with some random amount of stock, and we can take a list of actual customer orders. And then this is representative of where we might be when we start picking a batch of orders in the factory. We can loop through that list of orders and we play out the routing process, and we can keep track of how much stock is consumed by each order. But in this graph on the left, what we've got is an unbounded simulation where we're sort of assuming that we have infinite capacity in our model. So we're keeping track of the stock that we use, but if you look at the y-axis on the graph on the left, you'll see that actually a lot of the stations go below zero stock. And obviously this isn't representative of reality, but it's really useful because, for example, it allows us to estimate the size of the prize. So, how far below zero do we end up if we choose a particular strategy? Or we can use this to generate some data to look for bottlenecks elsewhere in our system. So we can say that the amount of stock that we have, we just pretend that it's never a problem, and we're trying to focus on what other problems we might have in the factory. But then on the right, we have the more realistic situation where the stations have finite capacities and the algorithm is aware of this. And then what you can see here is that the rate of consumption, which at each station is fairly flat on the left, you can see the gradients of the lines are constant. On the right, you can see that as stations start to run out of stock, the stations that do have stock, we really start hammering those. And so this is, as I said, a little bit more realistic and representative of how things behave in practice. But it's still, it's a really simple approach that allows us to extract some value, when modeling things in the real world in silico. So moving on to SymPy, as I sort of described it, the medium detail way. In reality, this is kind of best represented by however many hundreds of lines of Python code, but that doesn't make very good slides. So we've got this block diagram, and as I alluded to earlier, SymPy allows you to test, how multiple algorithms or processes interact and observe, final output metrics or feedback loops. So, for example, how a change in the Pickface optimization algorithm that Dom spoke about might impact the order routing algorithm or the flow of stock, and how that might in turn, impact where other orders can go. So here, we've got the outputs of two algorithms, and let's say we want to model those in detail. And maybe use some real data, but then let's say we also have just some sort of simplified business logic. So, some really simple rules about what happens at a particular time, and then maybe also some real world constraints. So, the number of people we might have available to do a particular task, or the throughput rate of a conveyor belt in the factory, for example. And then we can construct this SymPy model in code, and we can play it through, as fast or as slow as we like, and put detail on the bits we care about, and as I said, simplify the bits we don't. And that allows us to really rapidly assess a range of scenarios and a range of changes to algorithms, without having to do anything in the factory and without basically any risk. So again, just for a couple of examples, on the left, this is a graph of again, simulated availability of operatives in our factories. So what we've got here is that over time, as we approach sort of halfway through this simulation, we have basically all of our operatives just standing around twiddling their thumbs, and then we can change the process and see that suddenly our availability drops, and more of our operatives are actually, actually helping to put food in customers' boxes, which is what we care about. And on the right, it's a little bit messy, but here, we're modeling, as I said, the flow of stock around the warehouse. So this is a particular ingredient, how much of it we have at different places. And you can sort of just about see that, we have at particular times, we have, this ingredient arrives in a location and then it sort of immediately moves to another location. And you can see how the system reacts to, for example, the drain in these locations and how they're replenished, with stock from other locations. And again, this is data that would take us a long time to collect in reality in the factory, and that it would be very difficult to test a change to in reality, but we can do it, as I said, in silico. And then finally, as I said, maybe the most polished way, the sort of professional simulation software. As I said, this isn't a model of our factory, but you can imagine that it's sort of reasonably representative. We have conveyor belts with boxes going around the line, and so we can, for example, with our our new factory that's going to open soon, it's not physically built yet, parts of it, but what we can do is we can take the schematics and we can construct a simulation here, and we can pipe real customer orders or maybe simulated orders from the network simulator through it, and we can see how the proposed operational strategies will work. As I said, that might be completely differently to how we do things in our existing factories, and we can spot any potential problems before they materialize in the real world. And indeed we have already changed things about the way our yet to be opened factories will work based on these simulations. And I guess one of the most valuable things that this provides is this kind of visualization that we've got up on screen here, which is really useful. I mean, it's good for us as a team to sort of like visualize the way things work, and helps us understand and troubleshoot. It's very cool, it's just really interesting, which is definitely a highlight. And I guess most importantly, it's really good for stakeholder engagement. So ultimately, as a data scientist working in a business, you've got to get your stakeholders on board. And it's one thing to say, this metric reaches this particular value at this time, but even if you're dealing with technical stakeholders, but especially non-technical stakeholders, it's quite another thing to show them a video of boxes flowing around the new multi-million-pound factory, and then suddenly everything grinding to a halt because of a particular strategy. And so that's an example of the kind of value that you can get from this kind of thing, which, as I said, you can get a certain amount of that from something like SimPy, but yeah, using this commercial software, then we can provide real value to our stakeholders. And so that brings me to the end of to my talk about simulating at factories. I guess the only thing left to say is to say thank you, and as Dave mentioned, we'll be sort of like sticking around for a Q&A. And as Tom mentioned at the start, we're always hiring data scientists. I think our LinkedIn details are in the chat. Please feel free to reach out. And so let me hand back to Dave for the Q&A.
Awesome. Thank you very much, Daniel. Thank you also to Tom, Dom and Joe. And if I could invite you all to turn your cameras back on, come and join me on the Data Science Festival stage. So man, yeah, great session. I kind of tried to call it out at the beginning, but seeing how data science and data in general pieces together within an organization to drive that ultimate end goal, which drives the business forward, I always find super interesting. So thank you for sharing. We are going to jump into the Q&A. There has been a couple come in already, so thanks Julian for those. I have a couple myself, and we'll get into those as well. And then in the chat we have had Manish in the chat just saying amazing session as well. So yeah, please do fire a little thank you into the chat as well. It's always nice to have a little comment in the chat saying thanks. So appreciate that, Manish. In terms of the questions, where to start, man? Where to start? Maybe actually we will kick off actually with a couple from Julian, and we'll see where we go, and then we'll pick up some of my questions as well. We have also had Tom and Noor and Arthur jumping in the chat as well. Absolutely great presentation, guys. Thanks a lot. Noor, man, you are my absolute favorite. Noor, like Noor never misses a session. He's like number one, and I've not spoken to the team, Noor, but hopefully you're going to be there on the 27th. It wouldn't be the same without you. So let's see if Noor comes back and lets us know if you're going to be attending on the 27th. But in terms of these questions, guys, obviously there's 4 of you. Keen to take multiple inputs, or if it's best for one of you to pick it up, by all means, just kind of yell it out. Keep it nice and interactive as well. So we'll start with that top question there from Julian. Julian's passion is data quality, as it should be, Julian. So far, no one has mentioned data quality. Does this mean that you are one of the very rare organisations with no data quality issues? How do you account for real-world data quality of input data and the effect on the modelling and forecasts? So does anybody have an opinion on data quality at Gousto?
Yeah, I guess I can field that one. I don't think any of us would kind of, pretend that we're the rare organization that has perfect data, and I think we, we have pretty good data, but yeah, there are always certainly, problems when you're dealing with, as we said, with the physical world and with physical processes. In fact, so we have a team of people who are focused on data quality, and they do amazing work. We're always also updating our algorithms. So, you mentioned, forecasting. I know that the guys who work on forecasting, they put a lot of effort into, looking at the errors and looking at, the ways that things differed in the data that we see. And then lastly, having just spoken about simulation, we actually find that simulation is quite useful where, if we have a particular sort of like data set where we think the quality might be lacking, we can use a simulation to sort of, either to corroborate that or to compare against, and to add a little bit of extra sort of like validity to some of that data.
Perfect. Thank you very much. Talking about simulations, it did catch my eye when you were talking about simulations and A/B testing. So I'll be that's one of my questions to dig into, but I'll maybe come back to you on that in a bit, Daniel. So yeah, thanks for that question, Julian. I will now jump down to the question there from Zana. So Zana is asking, first of all, saying thank you for a great presentation, very interesting. They're asking, how do you forecast orders for new menus that you naturally don't have any historic data for? So how do you guys approach that when you have a new product and there isn't that history of data? How do you go about making predictions?
Yeah, I'm happy to pick this one up. So yeah, forecasting is a pretty ubiquitous problem for any company that sells anything to anyone. Yeah. So these are some like relatively well-trodden fundamental principles here. But what you're referring to is the cold start problem, which is also like quite ubiquitous in data science. So how do you make any sort of inference about a thing that you haven't seen yet in your training set? And the sort of intuitive answer is that you try to look for similarities between the thing you're trying to predict and the data you've already got. So a more like formal way to describe this is if you can come up with some sort of similarity metric or distance metric across the data that you've got between this new upcoming recipe that your customers have never seen before and your operation has never seen before, to other recipes that you've had in the past. Maybe this can be similarity in terms of the ingredients that are included, similarity in terms of the cuisine that it belongs to, similarity in terms of just any data feature of this new product entity. And then you can basically look at the trends from how those recipes previously performed in your operation, and maybe use those to sort of seed your inference about this new product. So that's generally how we solve the cold start problem.
Perfect. Thank you very much, Tom.
I'd just like to add to that real quick.
Yeah,
at that, like the time horizons that we need to make operational decisions, we often have information already about the orders that have come in. So we can start, we might do like some longer range forecasting of new recipes, but actually by the time we need to buy like, short shelf life ingredients, we might actually have a lot of new orders for that week. So we can get a lot of information from that as well. So we kind of get a big boost in the accuracy as we kind of see real orders come in, which helps a lot with our short-term planning.
Perfect. Thank you very much, Dom. And that is exactly what I'm looking for in this Q&A as well. If anyone has anything to add, like don't stand on ceremony and jump in. And I feel like we should redo this where we are actually on a stage, perhaps with a bottle of beer in hand, and really like let things fly a little bit. So yeah, cheers for jumping in there, Dom. I'll stick with the Q&A questions there as well. Anthony's questions just pinged up to the top there. Actually, someone's given it an upvote, which is quite a nice feature. Anthony's asking, how do you find the Simply package? Is it pure Python, I think, which may be a bit slower when running many simulations? Has that been an issue? So yeah, how do you find that package, and has there been any performance issues?
Yeah, I mean, you're correct that it's pure Python. I think probably the answer I'd give is kind of the answer, to why a lot of data scientists use Python, is that it's maybe not the fastest thing, but it is really flexible and really easy to use. And I think that for the sort of the time length that we need the simulations to run for, and for the problems that we simulate, it's been sufficient so far. Where we have bigger problems, or we want extra level of detail, as I mentioned, there's also, we use commercial software as well. But I think we really like SymPy because while it might not be the fastest, it's very, very easy for us to, develop and prototype really quickly.
Perfect. Question follows on there from Adnan, actually, which kind of leads in quite nicely. In picking obviously that as a solution, did you do a proof of concept to go with that? And if you did, what other frameworks or apps did you consider?
Yeah, I guess I'll take this one as well. Yeah, so it's kind of an organic growth of us using it. We started a little bit sort of side of desk work, and then started to see, as I said, some real value from it. So it kind of grew organically from that. We have investigated other ones, but we kind of keep coming back to SymPy. I can't off the top of my head, I can't remember the exact names. And then, as I said, we use the other software for the bigger factories that are opening.
Perfect. It's been a great approach, and it's not necessarily a question from the audience there. And again, just call out who this may be best for. But in terms of building, the network simulator, what were the main challenges that you came up against? And is there any learnings that you could share if anyone's considering similar projects?
Yeah, sure. So yeah, the challenges were sort of twofold, really. There was the first one being sort of understanding all of these data products, and not only how they work on their own, but also how they feed into one another.
Yep.
And essentially kind of building a theoretical understanding of what the network simulator should look like.
Mm-hmm.
And then is the second sort of main problem, which I believe was a far harder one to overcome, was that all of these, as I mentioned, all of these data products which were within the simulator were already pre-existing at Gousto.
Mm-hmm.
And they'd all been made at different times, and they had all been designed to quite different non-functional requirements. So there was a lot of differences there. So some of them, access data in different environments. Some of them, you could run locally on your computer. Others you'd need to connect to the cloud. So these differences really made it sort of quite hard in sort of integrating them all together. However, and you kind of mentioned, was there any learnings from this? And yeah, definitely. So I think the main thing here was sort of the desire to have a standardized sort of non-functional requirement specification. So how should your data products sort of be deployed, essentially?
Yeah.
And that is actually, in fact, something we are working on in Gousto now, is to get all of our data products built to these specified non-functional requirements, so that they are sort of easy to use and easy to sort of be integrated together with other products.
Yep, perfect, man. Thank you very much for that, Joe. I'll maybe come to you, Dom, actually, and bring you in. And again, as you were talking, you mentioned using simple simulations for your Pickface mapping algorithm. Is there any reason that you decided to do that against using exact optimization methods instead?
Yeah, so we did actually try exact optimization methods. When we approached this problem, we kind of came back to it about a year ago to try and do a new version of it and try to do it, but it actually turned out to be a very hard thing to kind of get an analytical objective function for.
Yep.
And the reason is that we're optimizing for throughput, but actually we're optimizing how we set up the line to then use another algorithm to route orders down it, and then to have obviously the real process of throughput in the factory with all the other things that affect it we can't really choose. So it's very hard to get a kind of direct objective function for that. So instead we found like simulating is probably the best way to do it. But because we do have a kind of understanding of what makes a good solution, we can generate solutions that are kind of good and use a kind of stochastic element to then create a large pool of like good solutions and evaluate them in any kind of complex way that we want.
Amazing. Thanks very much for that. I will quickly jump back into the chat, because as we've been talking, there's been a number of messages coming through, and it is always nice just to call these out. So Giuseppe there, great presentation. Ben, thanks everyone, great presentation. Anthony, thanks for the talks. Jag, great session, fantastic to hear data at the forefront of business operations. Michael, thanks for the talk. The list goes on. Ganapati, Lewis, Aidan, all jumping in saying how much they've enjoyed the session. So I'll definitely reiterate that. I will go back to the Q&A there, and we'll just perhaps have a bit of a quick fire through the Q&A and see if we can get through as many of these as possible for the people at home. The first question is coming from Zoom user. Oh God, I was going to make such a dad joke there and be like, that's not their real name, blah, blah. Sorry, I have to stop myself sometimes. Zoom user is asking, do you see any value in probabilistic programming, such as PyMC3, for your interfaces? I don't know who would be best to pick that one up.
Yeah, I'm happy taking that one. So yeah, there was something we explored a while ago. So obviously in the network simulator, I mentioned a product we had which predicted throughput. However, there is quite obviously as you open new factories and you have new lines, those production lines have very little data relative to the ones which have been open for a while. So yeah, we did explore the idea of using Bayesian hierarchical models to sort of account for that and basically sort of allow sort of using Bayesian inference to be able to train models on sort of lines which we had a lot of data for, and then sort of using the whole Bayesian updating thing to be able to sort of change those models slightly for new lines. And yeah, just sort of allowing problems which you don't have much training data for to be able to use sort of other models to guide them a little bit.
Right, perfect. Thanks for that, Joe. Keeping it going with the Q&A there, question from Jack Preston. How do you decide when to stop optimizing and tweaking your simulation models?
Yeah, I can take that one.
Cheers, Dom.
And to be honest, I have to say it just depends quite a lot on the circumstances. So obviously Dan talked a little bit about like different complexity simulation models. And I think ultimately kind of how complex it is, what you rely on it really affects this. So if you're doing something like super simple, which you're just trying to get, quickly validate an idea or just understand the direction of a problem, then you probably wouldn't optimize very much. You might make it quite simple. Whereas if it's something you're going to kind of rely on loads, then you're going to invest a lot more time in kind of making sure you think it's accurate and kind of as good as can be. So I think it really depends on kind of how much you need to trust it and then how much you're going to use that.
Perfect.
I guess the follow-up answer would be that we're kind of never done optimizing it. We can always we're always looking to improve our models and processes.
Data scientists at Gousto never sleep. I love to hear that, Daniel. Always optimizing. Question there from Julian. It's more, I guess, around like how Gousto works in general, which is potentially quite interesting. But Julian's asking, are customers close to a factory that cannot do the full list of recipes, only offered recipes that the local factory can produce?
So I can take that one as well. So the short answer is that we don't do that. So we kind of like bias towards offering choice for everyone. Mm-hmm. But it does kind of talk about quite an interesting trade-off, because you have kind of choice on the one hand, offering all your customers everything. On the other hand, you've got the kind of cost for us, because obviously the further that you have to go, the further that wants to be delivered, it costs more, there's more viable impact. But there also is a convenience factor as well. So like we want to ramp up our ability to kind of deliver on a shorter time scale. And it might be in the future that we need to say, well, actually, if you want to get your box in 2 or 3 days, you can have the full suite of recipes. But if you want to get it in 1 day or the same day, then you have to choose the factory closest to you, and you have a limited range. So I think it's really going to evolve in the future how we kind of deal with this trade-off.
Perfect. Yeah, cheers, Dom. Yeah, sounds interesting. Question from Stephen. Stephen saying, great session. Thank you very much. What is your deployment tech stack, and what do you find is the most agile way to deploy?
I'm happy to take this one. It's not the shortest answer in the world, but fundamentally we're running an AWS shop. We use Circle CI for continuous integration and deployment, which is triggered through GitHub. We use a lot of CloudFormation. So the idea is to provision and deploy a well-specified, fully capable data product to the cloud through infrastructure as code. And we typically empower our data scientists to own that part of the process as well. But we do have a well-developed platform team there to support. Recently, we have been experimenting with Databricks as well, which is like a fully fledged ecosystem for any and all data engineering, analytics, and science needs. And so we're definitely gravitating in that direction as well. But we've got a whole host of tools and many different ways to build what we need. So yeah, it's just about selecting the right tool for the job at the right time.
Perfect. Thanks, Tom. It's nice to have sponsors shouting each other out as well. So Databricks are another one of our sponsors. So I'm sure in the Databricks session, they'll be pushing Gousto and delivery boxes and stuff as well. So I'm going to jump. Actually, I will take this question from Julian because it's obviously pretty topical with COP26 having been on and stuff like that. And Julian's question is: does the carbon/environmental impacts of different scenarios feature in your models? And if so, how? I don't know. Is that a factor in the Gousto models now, or may it be a factor in the future? Do you know?
I'm happy to take this one. So, yeah, obviously, our forecasting team works very hard to minimize forecasting error, which obviously a large motivation for is to reduce food waste. But I think a really good example, which is more relevant to this talk, is our package Tom discussed earlier, which is to sort of find the most efficient factory to route boxes to. And in fact, one of the modules in this model is in fact to kind of route to the factory which has stock which needs consuming.
Perfect. Thanks, Joe. And I think, speaking with different people at Gousto over the years about reducing food waste and stuff like that, it's clear, you guys have definitely focused on that mission for sure. So there's a couple of final questions there in the Q&A. So we'll maybe pick those up and then kind of wrap things up from there. So I'll take the one at the top first from Giuseppe. Great presentation, guys. Can you describe a little bit how you collaborate within the squads and between different squads? How do you share knowledge and discuss hypotheses between data scientists and manage non-technical team members as well? So perhaps one for you, Tom, or is that for someone else?
I'm happy to take this one. We're probably similar to quite a lot of companies in we basically have squads of data scientists, data analysts, all kind of data professionals, also software engineers and product managers, all working together, and that kind of cross-functional way of work we find to work really well because it kind of means we're less siloed away, and it means we kind of have an easier time integrating with our overall kind of tech platform. And in terms of how we share knowledge, we have kind of regular team meetings, and we do internal presentations, all that kind of usual stuff you see. But also I think we just have a good culture of kind of internal blogging. So we kind of always write up a lot of our analysis, have good visualizations, and kind of post it on Slack so people can see. Yeah. And we just do a lot of collaborating together. So we obviously pair a lot, but everyone's very open to just, getting pinged on Slack, say, can you jump on call for an hour and discuss? And I think that's a good way to kind of share knowledge around the organization.
And in terms of sharing to non-technical members, we also have brown bag lunchtime talks and things like that. And we're also just sort of starting a series of sessions, sort of data bootcamp kind of sessions to do sort of knowledge sharing across the business.
Perfect. And do you find the non-technical staff are open to this? Are they all keen to learn more?
People generally are at Gousto, actually, as Tom said right at the beginning, that about the whole being a data company that loves food. Data has been a big part of Gousto since the beginning, since way before any of us joined, and I think that does kind of come through the culture and mean that people are generally kind of keen to learn and understand how it can help them in their jobs, even if they're not kind of specifically tech.
Awesome. Yeah, it's great to hear. Great to hear. We'll come to this question from Tom Paddon, just as the final question, and then we'll draw things to a close. Tom's basically saying, thanks for sharing your experiences. Other than COVID, what sort of real world issues or events disrupted operations in practice that were not forecasted by your simulations? And then further, are there any types of issues that simulations can systematically miss?
Yeah, I'm happy to pick this one up. So I think the appropriate quote here is, all models are wrong, but some models are useful. So there are, to be honest, innumerable things that our simulations fail to represent. We don't have a perfect representation of the real world. This is the nature of simulation. The And the important tactic is to make informed decision about what compromises you're willing to take. So continually measure and assess the extent to which your simulation quantifiably matches up with reality. And if there are big gaps, then go and observe your real system. In our situation, this means physically go into a factory, maybe even work a shift in a factory to get a deeper intuition of how the real world physical system actually works, and then try to embed those learnings into your simulation until you achieve sufficient parity with the real world. And the gold standard is always, can you drive some sort of measurable success or some measurable operational impact that is beneficial to the company? If you can do that based on your simulation, then that's the gold standard for whether your simulation is accurate enough.
Perfect. Thank you very much, Tom. That has been magical, chaps. So yeah, thank you all very, very much. It was great to learn more about how you're approaching things at Gousto. It was nice to have such an interactive session. We've managed to get through 11 questions there, plus a couple from me, which is good, and really enjoyed it. So thank you very much for being part of this year's Data Science Festival. I did mention at the start, I do know it's not just coming and sharing your Tuesday evening with us, it is also actually the time to prepare and all that sort of stuff as well. So yeah, thank you all very much. Hope you had a good time. How did you find it? Is everyone happy, basically?
I'm happy.
Yeah, thanks for having us.
Thumbs up.
Thank you very much.
Everyone's smiling. That's all good, man. Well, thank you all for joining us at home as well. Hopefully get to see some of you at future online events, and you never know, maybe even at an in-person event. And if you are at an in-person event, please do come and say hello. It'd definitely be great to see you all in person. But yeah, thank you all very much for tonight, and we will see you all very soon. Goodbye.
Thanks so much for having us. Bye.
Thank you.
Cheers,
Bye.